Hi folks, this is the third video segment that I'm doing for explaining how a base excitation or restraint excitation problem is handled in modeling a single degree of freedom system within Catia. In this example, I'm assuming that the car is traveling down a road which is bumpy, so it's a car traveling down a rough road. Let's think about it like that. And let me actually start this in the following mode. The amplitude of this road profile is half this uh, peak, maximum to minimum value. So if this maximum to minimum value is 0.02 meter, or let's say 2 centimeter, then the amplitude of the oscillation of the base is actually half of that, 0.01. By the way, I call these the killing of a fly with the cannon series because these are standard problems that are discussed and solved in any elementary vibrations book. And the purpose of CATIA is not, or the purpose of the FEA module embedded in CATIA is not to solve simple problems of this type. Okay, there are more effective ways of doing these things. There's software specialized for this kind of a vibration analysis. But anyway, we're going to try Catia. Now, this car is traveling down that track, down that road at a velocity v, and because of the bumpiness of the base road, this massless base is being pushed up, and therefore the mass starts to vibrate, and the whole objective of this problem is to find out what are the, for example, the displacement of the mass, the velocity of the mass, etc. Now, let's assume that it's a sinusoidal profile, as I said, so the amplitude is 0.01, half of this maximum to minimum value, and the frequency of the oscillation of this base, massless base, is, we call it omega b. Omega b, you can easily relate it to the velocity of the car by making conversions. For example, if the velocity of car is specified in kilometers per hour, then this is the way it's going to be. This is going to be circular frequency of the oscillation of the base. Okay. Now, the following parameters are going to be used here, and C is given directly, so I have to find the damping ratio, which is right here, 0.498. And if I use the data that it's the car is traveling at 20 kilometers per hour, you're going to get omega b equal to 5.818 radians per second. Now, I also want to point out to you that we are interested in the steady state response of the car. In other words, the car is going along that track for a long time. Everything is going to reach the steady state, and our objective is to find out what is the steady state motion of the car, or the chassis of the car. This is the chassis of the car. Now, it is known that well, based on elementary differential equation, this is going to also oscillate up and down sinusoidally with the same frequency as the base frequency. Okay. Now, so let's write down some of the stuff that we know. In the case of this problem, if you know the profile of the road like this, and if you differentiate it twice, you're going to get the acceleration of the space, okay? So it's going to be a negative y times omega b squared, because you differentiate sine twice, you're going to get omega b squared, and you get the sine back. And the compartment, the chassis, is going to oscillate at the same frequency, except that the amplitude we have to be able to calculate. And these type of things are done in, as I said, elementary vibrations book. So the amplitude of the vibration of the compartment in terms of the vibration of, or the amplitude of the base road profile, is given by that. The natural frequency is, of course, square root of k over m. It's this, and you need that because in order to calculate big X, you need this frequency ratio, which is the ratio omega b over omega n, which happens to be 0.292. Now, if you take r equal to 0.292 and the zeta equal to 0.498 that I have in the previous page, and you stick it in there, and of course y being 0.01, you're going to get the amplitude of the vibration of the compartment as 0.011. Okay? Approximately. Now, if you take that stuff and plug it in the expression for x right there, you're going to get this. And of course, the base acceleration of the base, up and down acceleration of the base is based on the numbers that you have calculated is right there. So big Y omega b squared is going to give you that number. Now, the relative displacement on compartment is this difference between the little x and little y, okay? Because little x and little y, these are the displacement, absolute displacements of the compartment and the base with respect to some fixed coordinate system, okay? So the relative displacement is going to be x minus y. And if I plug in the values that I just know, basically the relative displacement is just a very small number, 0.01 sine of this, because notice that these are the same sinusoid, it's just the difference of these two amplitudes. Now, when we do this problem as a base excitation problem, because the motion of the mass is taking place because of the motion of the base. So it's a base excitation problem. So what we need to do is basically tell the software what that acceleration of the base is. And remember, acceleration of the base was a sine function, okay, and multiplied by 0.33, which was omega b squared times y. So this is my modulation curve that I'm going to, time modulation curve that I'm going to give Catia. And if you just right here, 0.338 is going to be the time modulation curve right there times that coefficient 0.338. Okay. Now, I have plotted these things analytically. Remember, we're going to be using a spring rigid type of connection, as I have done in the last 11, 12 video segments on this topic. And these are the generated plot, not by Catia, the analytical solution that we just showed you for different entities. And so we're going to compare the Catia problems, Catia results with these curves. Okay? All right. Let's go ahead and do that. I just want to make sure I remember what these things are. So the mass is almost a ton. This is 400,000, K is 400,000, and zeta is 0.498. Very good. So let's go ahead and create our standard points. This is a single degree of freedom. We need 2 points right there. Another one, let's say, I don't know, maybe 0.5, 0.3 meters right there. These are totally redundant, or not redundant, you have to do it, but irrelevant to the calculation, but you need to do that. I'm going to create a line here, and then I'm going to apply a dummy material to that. I'll apply aluminum, but this is treated as dummy because I go and reduce the Young's modulus of the aluminum by 7 order of magnitude. So this is going to be 0.1 instead of 10 to the, I don't know, 9, 10. It's going to be 0.1. And the density of it, instead of being 2,700, is going to be 0.1 kilogram per meter cube, essentially lighter than air. Now, this is basically a geometrical model. So we're going to go to generative structure analysis. We're not going to do a static analysis. We do frequency analysis. Okay, and before I forget, let me go ahead and change the number of frequencies expected from 10 to 1. Otherwise, you get this error message saying that you don't even have 10 frequencies. Why are you trying to extract them? Now, I'm going to hide these points. Okay. Good. And mesh this thing with beam elements, but minimal number of elements, just one element through that length, because it is needed but it's not going to be coming into calculation. And then the cross-sectional area is a dummy cross-sectional area made at circle. Doesn't matter what the size of it is. That's done. Now we're going to create our connection, analysis connection between this point and for the second component, that point. Okay, it's right here. It's created right there. You can see that. And we're going to turn this thing into a user using a user-defined distant connection property to a spring. So you click on that, and the only thing that you can pick from the tree is just that connection that you just created, and you click on the wrench, and for the stiffness of the wrench in the y direction, you put down 400,000. Is it 400,000? Yeah, 400,000 Newton per meter. That is this number right there. Okay, good. Okay, so we say okay, and we close this. Now let's put a mass there. So here are the masses, lumped masses, Catia called distributed masses. You click on it, you put on this, and the value is 1007 kilogram. These are the numbers that are already put in the software because I made a trial run on this video, so I put the right numbers in there. But anyway, this is the mass of the compartment or the car or the chassis. What is called the sprung mass. Okay, the sprung mass of the car. Now, restraints. So you click on the clamp. This end is clamped. And this is going to move only in the y direction. That's why it becomes a single degree of freedom system. Only displacement in the y direction. Okay. And I hope I didn't forget anything, but that's pretty much it. So let's go ahead and find the natural frequencies. You click on the compute. There is really not much to it. There's only a single frequency that's going to get extracted, and that is going to be the natural frequency of the system, which is in hertz 3.172. That is actually that 19.93, but 19.93 is actually radians per second. You divide this thing by 2 pi, you're going to get that number that I had 3 point something. All right, good. So let's go ahead here. Now we do the rest of the problem. We're going to have to insert a transient dynamic response case. Remember, Catia's dynamic capabilities are based on linear dynamics, and that's what we're doing, linear dynamics. That's why you need natural frequencies. So it's not a load excitation, it's a restrained excitation, not a load excitation, restrained excitation. But for the reference frequency is the thing that we just calculated. See that? We just calculated frequencies right there, so we put it in there, and you make sure there's restrained excitation. You click on it. Now, if you go to the damping, if you go to the damping line, double click on it, click on the wrench, the default is 1%. We found out that this thing was actually, we calculated this, right? Yeah, it's 0.498, which is 49.8%. So let's go ahead here, put 49.8, 49.8. This is a very heavily damped situation, but that's okay. Now, you click on the transient, this line, transient dynamic response. We don't want to do the simulation over 10 seconds. We want to do it over roughly 1.5 seconds. So that being the case, we're going to put the 1.5 here, 1.5. And 20 is, remember, this 20 essentially gives you the accuracy of the result and the choppiness of the result. 20 may be very low. It is very low. So what people usually do is start with 20, they go with 40, and then it's 68 until things don't change anywhere. But I don't have the patience of doing that right now. So we just do 1,000. Good. Now, restraint excitations. Now, I don't have anything to do with Tx and Tz. We're only concerned about displacement in the y direction. Now, as far as the modulation is concerned, is that sine curve that I said we have to import, except that I haven't done it, so I will be doing it. And this number is going to be the modifier omega b squared y, big Y, omega squared big Y, which is 0.338. or minus. If the curves don't come out the way we want them, you can make it minus. It really doesn't matter, okay, because you're dealing with steady state situation. So you can put a minus 0.338 or 0.338. It doesn't matter. So that is the number that we're going to put. I'll put a minus 0.338, and it's the unit of acceleration, and so there we are. And for the modulation, I don't have one, so I say okay, because I don't want to, cancel that. Say okay, let's go and import our modulation right there. On the modulation, time modulation, you click on it. It says, where is it? Where did you put your Excel spreadsheet? Well, I put it here. It's called base excitation, car over rough road. You say okay. Just give it a second and then say okay. In fact, this will appear in our tree right there. You put the cursor there, right click 2D, generate 2D display. We want to make sure that it is actually what we want over 1.5 second interval. So we close that. All right, good. So let's go back to our restraint excitation that we left off right there for the second line for TY. For the selected modulation, we're going to select this thing that we just imported. And we say okay. That's pretty much it. Now, in the previous two videos, I showed you that because you're interested in the relative stuff, relative displacement, relative velocity, etc., what you need to do is you have to go in the sensor, right click and say create create global sensors. Oops, sorry. Not just a second. Just 1 second. Create global sensors. Let me see, something is okay. You put the sensor, you put the cursor on sensor, right click. I'm looking for local sensor, but see, when I let's say yeah, let's actually say update all sensors. Okay, right click. I'm looking for this local sensor, but unfortunately it's grayed out. So let's actually make a run. I didn't anticipate the need for running. Do I have it now? Yeah. I it looks like, at least in this problem, I had to go and just compute it, okay, because it could not find that create local sensor. So I ran it and now it disappears. So if you click on it, now what do we want? We want relative displacement vector. Scroll down with the control key down, relative velocity vector and relative acceleration vector. Okay, and let's do this is the global vector, so we say okay. So these sensors are created here, except that I have to go and define them. So let's go ahead and do that. So I'm going to double click on this. It says this was the relative displacement. It says, where is it? I want this point, this vertex. And I'm going to do this thing one by one. Okay, so we say okay. Notice that this is still in the update mode. So right click, update sensor. Say fine, do it. And once it's done, the update sensor update sign is gone. So you put the cursor there, right click, and generate 2D display. Okay, it says, well, where right here. Okay, so this is, yeah, so this is our this curve is our relative displacement. Now, first of all, let me move this thing on the side. I don't like it here. You put the cursor, options, on the title, not top left, top center. Okay, good. At least it's not going to block my view here. And let me move these things out of the way. I don't need any of these, so I'm just going to move it out of the way so I have a nice, clear, clean view. Okay, let's put it up there. Okay. So notice that this is to be compared with let me actually do the following. Let me actually capture this view.